It's a pleasure to introduce the first speaker of this afternoon session, Abramo Hefez from Federal Fluminense. I remind you that Abramo's idea was was Abramo who created this workshop on on algebraic singularity theory in 2002. Right, wrong, that you helped me to remember, 2002. So it's a great pleasure, Abramo. It's Value Sets of Fractional Ideas, the title of his talk. Thank you.
Well, thank you, Cidinha. I would like to thank the organizers for the invitation. And it's a pleasure to be a speaker in the first version of the workshop outside UF. Well, I'm going to talk about value sets of fractional ideals, and I will explain what does this mean and why it is important to study them. And well, I have been working on this subject almost more than 3 years, and it has grown during this time. Well, I will explain what are our objects. Our objects are admissible rings that generalize local rings of curves at singular points. Okay, this is a generalization of the local ring of a curve at a singular point. Well, admissible rings are local one-dimensional Noetherian Cohen-Macaulay ring with the following properties. It is analytically unramified, and this is the explanation. What does it mean? It means that its completion is reduced. It is residually rational. Well, this is the meaning of that, and has a large residue field. Okay? This means that the cardinality of the residue field is greater or equal than the number of DVRs in the total rings of fractions of R over R. An important feature of these rings is that they carry value function in which you can measure the value of an element in the total ring of fractions of R. And this is a vector of length R, which is equal to the number of DVRs, the number R of GVRs, of extended integers. It means that there are integers, including the infinity. And the value h of such an element of the ring of fractions is the value in each DVR of Q over R. So this is a vector. And the fractional ideal is an R module inside the total ring of fractions for which there exists a common denominator. This is a non-zero divisor in R such that GI is inside R. In the set of fractional ideals of R, besides the obvious operations of sum and product, we have a column operation. It's usual column operation in commutative algebra, which means that J colon I is the set of X in the total rings of fractions such that X times I is inside J. Okay. For I different from 0. Okay. And there is a canonical isomorphism between this column, J colon I, with hom R I in J. Okay. fractional ideal will be said a canonical ideal if you have this property. K is a canonical ideal if and only if K colon I is equal to I. This is by duality for all fractional ideal I. Admissible rings admit canonical ideals, and two canonical ideals differ by a multiplicative regular factor in Q. Okay? This is the existence of the canonical ideals for this kind of rings. I guess it was proved for the first time by Danna. Examples of fractional ideals are R itself, the integral closure of R in Q, and the conductor ideal of I, which is I colon the integral closure of R, and this sits inside I. Duality. Usually, the dual ideal of a fractional ideal is taken with respect to R, which means that you take I dual, its home, over R from I to R. Or with respect to canonical ideal K, which is I star, is home from I to K. And what we are going to do here is to consider more general duality with respect to an arbitrary fractional ideal I, J, sorry, which is J column I. So you fix J and you let I vary, okay? And the dual of I with respect to J is just J column I. Well, a ring R will be called Gorenstein if R itself is itself a canonical ideal. This is a characterization, one of the characterization of Gorenstein rings. This means that the double dual of I is I for every fractional ideal I, with duality with respect to R, this duality. Value sets. Well, if you take a fractional ideal I, you define the value set of I as the set of values, we call it EI, we denote it by EI, and this is a set of values of the elements of I. So this is a subset of Z union infinity R times. I remember that R is the number of GVRs inside Q. ER is a semigroup called the semigroup of values of R, while EI for general I is a semigroup ideal. It's not a semigroup, it's not closed under addition, but if you take an element from the semigroup of values and you sum it with an element of EI, you end in EI. Okay? Well, why are fractional ideals important? Well, the importance of fractional ideals and of their value sets stems from the fact that they carry important intrinsic algebraic information about the structure of the ring R. These are combinatorial objects attached to the ring R, and we'll see how the combinatoric of these sets of values will reflect properties of the ring. For example, the fact that R is Gorenstein may be detected by duality properties of its fractional ideals, and as well by symmetry property of their value sets. I will explain this a little bit later. In the case of curves, there are some important fractional ideals as the Jacobian ideal, the module of regular differentials, and the module of logarithmic residues of logarithmic one-fourths, which possess duality relation among them and give important invariants. For example, the Turina number for a complete intersection curve is expressed as the codimension of a fractional ideal. Such codimensions may be computed via the value set of the fractional ideal. So we give some results concerning these computations. We consider the order product in the Cartesian product of extended integers, and sets of values E have the following remarkable properties. And the first property is that if you take two elements in a value set, the minimum of these two elements also belongs to E. Minimum, the minimum element between alpha, the min of alpha beta, is a vector which is formed by the minimum of each component is the minimum of the components of alpha and beta. Okay, so it's a product order in ZR. Second property is an existence statement which says that if alpha and beta are in a value set E, and alpha is different from beta, but they have a common coordinate, alpha I is equal to beta I for some I, then there exists an element in the value set in E such that, this element gamma, such that gamma E is bigger than the common value of alpha E and beta E, and gamma is greater or equal than the minimum of alpha and beta. And the third property is there exist elements gamma in NR, the nth power of the natural number, and alpha in ZR, such that gamma plus NR is inside E, which is inside alpha plus NR. Okay, this is important because this says that the least element satisfying the lower inclusion is called the conductor, which means that there is at some point of E such that the how you call it, trihedron, the upside trihedron is contained in E. And we denote the conductor by C of E, and the greatest element alpha satisfying the upper inclusion is the minimum of E. There's a minimum element of E. This everything taken in the product order of ZR. The Frobenius vector, this is a vector which will play a role of E, is the vector f of E, which is the conductor is a vector, minus 1, 1, 1, R. This is 1, sorry, this is 1, it's not R. 1, 1, 1, 1. Value sets are combinatorial objects attached to fractional ideals. And as usual, their understanding depends upon several notions we will define. This is the price we pay for working with combinatorics. You have to define several objects and then use them to prove your results. Well, we put I, the set of indices from 1 to R, which is a number of DVRs. This number, when your ring is a complete ring of a singular point of a curve, of an algebraic curve, this R is the number of branches of the curve. Okay? And we let J be a subset of I, which is ordered in increasing order. And for every J, which is different from empty set and different from I, we define the projection, the J's projection, which is you select from alpha 1, alpha R, just the alpha Ji corresponding to this set, subset J. Okay? And the J fiber of alpha is this set, Fj E alpha, is the set of elements of E such that the projection, the jth projection of beta coincides with the jth projection of alpha, and alpha I is bigger than beta I for all I in the complement of J. Okay? So they coincide. The elements of this fiber, J fiber, they have J's projection that coincide, and the other components are bigger than the components of alpha. And the fiber of alpha is the set, well, is the union of the Fi E alpha when this subset J is just one element. Okay. Well, what does it mean? Well, a sample of the importance of this notion is given by the following result, which is a result by Danna in 1997, which says that there is a unique canonical ideal omega 0 of R such that this canonical ideal is in between R and the integral closure of R, and the value set of omega 0, which I will call E0, is a set of alpha in ZR such that the fiber, this fiber here, of ER, in ER, in the set of values of R, of this vector, which is the Frobenius of R minus alpha, is empty, is the empty set. This is a characterization of the canonical ideal in terms of value sets. Okay, now the problem is how to determine E of I. The relevant information about a value set is contained in the the polytope, I will not call it hypercube, the polytope, which is a set of alpha in ZR, which are in between the minimum of E and the conductor of E. We have a polytope, and inside this polytope, all the information you need about the set of values is inside this body. Well, this could be a very big set. Okay? But fortunately, there is a much smaller subset of B that retains all the information about E. And this set is the set of maximal points of the value set. And the definition of maximal points is simple. It's a set of alpha in E in the value set such that the fiber of alpha in E is empty. What does this mean? This means that there is no element in E with one coordinate equal to the corresponding coordinate of alpha, and the other ones are bigger. Okay? This is the meaning of the fiber is empty. Well, maximal points are computable. This is the good thing about our object. So let us describe a little bit more the maximal points. We will define two numerical functions, which are P E I, E alpha, is the maximum of n such that the jth fiber of alpha in E is empty for all j inside I with the cardinality of j less or equal than n. Okay. So you start with fibers over j with one element, and this is empty, and then you go to j's with two elements, and all these fibers are empty, and so on, until you get the maximum of this n such that you have empty fibers. Okay, and q e alpha, it's kind of dual of p, is the minimum of n such that the jth fiber of alpha is not empty, so the converse, and here you have j, the cardinality of j bigger or equal than n instead of smaller or equal than n. Okay, one has that p is less than q, alpha belongs to E if and only if q E alpha is less or equal than R. Alpha is a maximal point of E if and only if you have that P is less than Q. This is, well, this is always true, but P is bigger or equal than 1 and Q is less or equal than R. Okay? This is the characterization of maximal point using this numerical functions P and Q. Now we have a definition. We call a maximal point alpha of E an absolute maximal if P of E alpha is equal to R minus 1 and Q E alpha is equal to R. Absolute maximals means that the fiber means that all fibers of dimension greater or equal than 1, or all fibers are empty. Okay? This is what means that P E alpha is R minus 1. Means that all fibers, all J fibers for any J are empty. A maximal point of alpha of E is a relative maximal if instead of that P E alpha is 1. This means that the fibers of higher dimension, highest dimension, are all empty, but all the other fibers are not empty. Okay, this is a relative maximum. And then you have the maximal of type PQ, for which P is PE alpha greater or equal than 1, and Q is QE alpha less or equal than R. Okay, so you have lots of types of maximal points. Usually, in the literature, you find only absolute and relative maximals. So we aggregate all these maximal points in our definition. The set of relative maximals of E determines inductively E in the following ways. So there is a combinatorial way to generate, to describe the value set E. And this is a result by Delgado in '87 in the case of semi-group, but you can extend it easily to value sets of fractional ideals. And it says that if you take delta, delta is the set of points in ZR such that the projections of alpha with respect to J with R minus 1 elements belongs to the projection of E. So this means that you take a point alpha, you want to know.
You fix E.
You fix E, yeah.
So delta depends on E.
Yes. Okay. Delta depends on E. So you take a point alpha in ZR, and you want to know if it belongs to E or not. So first thing is that the projections must belong to the projection of E. Okay? And then you have that this alpha does not belong to delta, but does not belong to the fibers of relative maximal points. Okay, so if you know the relative maximal points and you know the projections of E in codimension 1, then you know E, the set E. Okay? So the determination of E is inductively done by the knowledge of, well, you must know the projections of the value set, and you must know the relative maximal points of E. If you know that, you know E. Symmetry. If you take two fractional ideals, I and J, you always know that the dual of I with respect to J, which is this set, well, the value set of the dual, is contained in this set here, the beta in ZR, such that the fiber in EI of the Frobenius of J minus beta is empty. Okay? This is always true for every I and J. Well, the equality here in this inclusion is something very special. And the theorem is that the following are equivalent. J is a canonical ideal if and only if the value set of the dual of I with respect to J is equal to this set. So equality happens if and only if J is a canonical ideal. So you can determine the value set of the dual only when J is the canonical ideal. Otherwise, you know only that you have inclusion.
Is this a good criteria to determine whether J is fractional or the other way around?
Well, it's a criterion to determine if it's canonical.
Yes.
Yeah, okay. Yeah.
Is it effective?
Yes, it's effective. Yeah. Well, the implication 1, I implies 2, was previously proved by Delphine Paul in 2019, when J is the special canonical ideal omega 0, canonical ideal omega 0. So there is a long work to do to prove the converse. And the corollary is that the following are equivalent. E of R colon I, which is E of the dual of I with respect to R, is the set of beta such that you have this equality if and only if R is Gorenstein. This is a characterization of Gorensteinness.
So R is always admissible.
Admissible ring. Dimension 1, Cohen-Macaulay, etc., etc. Okay? So the fact that you have for R this equality of the value set of the dual is exactly this set, this is the equivalent to B Gorenstein. It's for every I. Well, let's see another criterion. This was a good criterion, but this one is a new one. For fractional ideals E and J, I and J, we define this number, which this is rho, it's not P. It's rho J I alpha plus 1 is equal to P, the numerical invariant P we defined, P E I alpha, the numerical function, plus Q E of the dual of I in the dual of I of the Frobenius of J minus alpha. Okay. And the fact is that we have the following result, which says that for all fractional ideals I and J and all alpha in ZR, we always have this inequality. Rho J I alpha is bigger or equal than R. So this number, rho J I alpha, is this number minus 1. Okay? It's always bigger or equal than R, with equality holding for all I and all alpha, if and only if J is a canonical ideal. This is another characterization of canonical ideals. And we have the following corollary. The following are equivalent. It's rho R I alpha is equal to R. Notice that now we are taking J equals to R, is equal to R for all I and all alpha, if and only if R is Gorenstein. This was proved, this corollary, by Delgado, Kiek, and Campillo in a paper. And we get this as an easy corollary, an immediate corollary of our result. Well, this is important. The importance of this is that it gives us symmetry of maximal points. And the theorem is that if I and J are fractional ideals, and suppose that alpha is in the value set of I, and the Frobenius of J minus alpha is in the set of values of the dual of I, then alpha is maximal. You have to impose that alpha belongs to EI and Fj minus alpha belongs to the dual. Then alpha is maximal in EI if and only if Fj minus alpha is maximal in the dual, in the set of values of the dual. So you have correspondence between maximal points of set of values of an ideal and sets of values, maximal points of the set of values of the dual ideal. Okay? Moreover, if alpha is a maximal of type PQ, okay, P EI alpha and Q EI alpha, then F, the Frobenius minus alpha is a maximal of type P prime Q prime, okay, of the set of value of the dual, where P prime and Q prime are given by this values function. Okay. And this has a corollary. And suppose that J is a canonical ideal now. This is for any pair of ideals. And now you suppose that J is a canonical ideal, then alpha is maximal of EI if and only if Fj minus alpha is maximal in the dual, in the set of value of dual. You don't have to impose the two conditions. In the above result, you have to impose that alpha belongs and Fj minus alpha belongs to the set of value of the dual. But now, if alpha is a maximal point of EI, this implies that Fj minus alpha is a maximal point of the set of values of the dual, and vice versa. Moreover, alpha is of type PQ if and only if Fj minus alpha is a maximal of type R plus 1 minus Q, R plus 1 minus P. This gives the complete description of the relation between maximal of the set of values of an ideal and the set of values, the maximal points of the set of values of its dual. And it's general dual. Here, this is a general statement. And this corollary is a theorem of Delgado, but only for absolute and relative maximals. They don't lead with maximals of type PQ. Okay, so you have duality in Delgado's work. You have duality between absolute maximals of the value set of an ideal and the relative maximals of the set of values of its dual and reciprocally. Okay. Okay, open question. One of the equivalent conditions that characterize the Gorenstein ring is that the conductor of ER, the conductor of the set of values of R, now this is the semigroup of values, is equal to the length of the quotient of the integral closure of R modulo the conductor ideal. Okay? And this is, well, the result is that this number is twice the length of the quotient of the ring by the conductor ideal. This is one of the incarnation of Gorensteiness. Okay? According to a result by Delgado, this is translated as the symmetry property of the semigroup ER. And the symmetry property says that for every alpha in Z, alpha in ER, if and only if the fiber in ER of the Frobenius of R minus alpha is empty. This is the symmetry of the semigroup of values, which is equivalent, as shown by Delgado, to the ring B Gorenstein. When R is equal 1, this last condition translates into the following result by Kunz. This is the usual symmetry property for numerical semigroups. Numerical semigroups are symmetric if for every alpha in Z, alpha belongs to the semigroup of values, if and only if Frobenius minus alpha doesn't belong to the semigroup of values. Well, this property was discovered by Apéry for plane branches. Okay. And then generalized by Kunz for curves in any ambient space. Notice that in this case, the Frobenius, which is the conductor of the semigroup of values minus 1, is odd, because the conductor is even. So if you take 1 from it, it becomes odd. Okay? And the generalization of Gorenstein rings are the so-called Kunz rings, for which you have almost the condition of being Gorenstein, which means that this length is twice this length plus 1 instead of equal. Okay? And it is known that R is Kunz domain. Kunz domain means that R equals 1 if and only if the semigroup ER is pseudosymmetric. That is, Frobenius is even, and for every alpha in N and alpha different from half of the Frobenius, alpha belongs to ER if and only if the Frobenius minus alpha doesn't belong to ER. This is the symmetry condition, but in addition, you have to put that alpha is not equal to half of the Frobenius, okay? And the question is, what is the condition on ER for R to be Kunz ring when R bigger than 1? We don't have an answer yet to this problem. So you have a characterization of Kunz domain for R equal 1 in terms of the semigroup of values. But when R is bigger than 1, we don't have this characterization. It should be possible to have this characterization. And one can formulate several similar problems translating properties of the ring into properties of the value set of its fractional ideals. Okay? And to finish, we are going to talk about co-length of fractional ideals and how one could compute the length of the quotient of two fractional ideals in terms of the set EI and EJ. Well, the motivation comes from the simple formula for R equals 1, which says that the length of the quotient of these ideals is exactly equal to the cardinality of the difference of the sets of values. Okay? But this doesn't work when R is bigger than 1 because you don't have numbers here. And, well, it's not true. Dana in 1997 gives a method relying on finding length of maximal path in the hypercubes B1 and B2 inside EI and EJ, but this implies that one has to know all the points of B1 and B2. So you have practically to know all the semigroup or the value set of the fractional ideal. Well, but since EI and EJ are determined by their relative maximals, it is reasonable to expect to determine the length of this quotient by using these points. And indeed, since the length of the quotient is equal to the length of I modulo I gamma minus the length of J modulo J gamma, for gamma big enough, where I gamma is the set of elements of I which are bigger or equal than gamma. So it's enough to give a formula for one of these numbers, okay? And we have the following result. For a fractional ideal I of a ring R with R minimal primes with value set E, one has that the length of I over I gamma is this sum, the sum of gamma I minus alpha I0 minus this number minus theta I, where alpha 0 is the minimum of EI, so these are the coordinates of alpha 0. Gamma I are the coordinates of gamma, and this number here is the number of gaps of the set of values EI, which is a projection of E on one of the components. Okay? These are the gaps of this set of values, and EJ is the projection over J of EI. So what we have here is this formula where theta 0 is 0, and theta I is the number of elements in this set. So this set is completely determined by the relative maximals of all the projections of E by J, the projections by J. So if you know the relative maximum of E and of its projections, you have the formula to calculate that number. And finally, we use this formula here to determine an additive formula for the Turina number of a complete intersection curve singularity in terms of the Turina numbers of the components. Okay? Since the Turina number is just the length of R modulo J, where J is a Jacobian ideal. Okay, so you use this formula to compute this, and this is an article we have just posted in archive if you are interested to. Okay, this is